Addition of 0.643 gram of compound to 50 ml of benzene with the density 0.879 gram per mole lowers the freezing point from 5.15 degrees centigrade to 5.03 degrees centigrade. If Kf for benzene is 5.12 Kelvin kg per mole, calculate the molar mass of the compound. They have given us mass of compound which we add to benzene. So this compound is solute. So its mass is written as W2, which is 0.643 grams. They have given 50 ml of benzene. And so volume of benzene is given, which is equal to 50 ml. Also they have given us density. So density of benzene is equal to 0.879 gram per ml. Using the volume and density, we can calculate mass of benzene. So therefore, we have mass of benzene, which is its volume multiplied with density. That is equal to 50 ml into 0.879 gram per ml. That's equal to 43.95 gram. So this mass of benzene is represented as W1. They told that the freezing point is lowering from 5.15 degrees centigrade to 5.03 degrees centigrade. So we observe depression in freezing point, that is represented as delta TF, which is equal to 5.15 minus 5.03, which is equal to 0.12. This difference can be written in terms of Kelvin, that is 0.12 Kelvin. Kf value is given, which is 5.12 Kelvin kg per mole. So we know that depression in the freezing point delta TF is equal to Kf into molality M. So the formula can be written as delta TF is equal to Kf into W2 into 1000 divided by M2 into W1. Substituting all the values into the formula, delta TF is 0.12, which is equal to Kf is 5.12 into W2 is 0.643 into 1000 divided by M2 is what we have to calculate, which is the molar mass of the compound that's added. W1 is 43.95. So therefore, we can write M2 is equal to 5.12 into 0.643 into 1000 divided by 0.12 into 43.95. So now let's simplify this. After simplification, we get M2 as 624.22 gram per mole, which is the molar mass of the compound that's added, which decreases the freezing point of the benzene. Vapor pressure of pure water at 298 Kelvin is 23.8 mm Hg. 50 gram of urea is dissolved in 850 gram of water. Calculate the vapor pressure of water for the solution and its relative lowering. So here we can make use of Raoult's law. So we have solute and solvent. So parameters related to solute, we shall represent it by subscript 2, and the parameters related to solvent, we shall represent it by subscript 1. So we are given with vapor pressure of pure water. Water is solvent. So vapor pressure is denoted by P1. So since it is for pure solvent, we'll write it as P1 naught, that is 23.8 mm Hg. They have given 50 gram of urea is dissolved in 850 gram of water. we have weight of solvent, that's water, which is W1, 850 gram. Also they have given 50 gram of urea is dissolved, which is weight of solute, is equal to 50 gram. We need to calculate vapor pressure of water, that is P1, also relative lowering of vapor pressure. Now let us write down the molar mass of water. Molar mass of water, which is a solvent, so therefore it is M1, that is 18 grams per mole. Molar mass of urea, formula of urea is NH2CO NH2, 2 into atomic mass of nitrogen, that is 14, plus 1 into atomic mass of carbon, that's 12, plus 4 into atomic mass of hydrogen, which is 1, and also we have 1 oxygen, so 1 into 16. So this is equal to 28 plus 12 plus 4 plus 16, which is equal to 60 grams per mole. And from Raoult's law, we have P1 naught minus P1 divided by P1 naught, which is equal to W2 into M1 divided by W1 into M2. So let us substitute all the data into the expression of Raoult's law. We have P1 naught, which is 23.8 minus P1 is what we need to calculate, divided by P1 naught, that is 23.8, which is equal to W2, which is 50 grams, into M1, that is 18 grams per mole, divided by W1, which is 850 grams, into M2, which is 60 grams per mole. Let us simplify the right hand side part. So let me write left hand side part as such. 23.8 minus P1 divided by 23.8 is equal to 0.018. So from this we can write 23.8 minus P1 is equal to 0.018 into 23.8, and therefore P1 is equal to 23.8 minus 0.018 into 23.8. This is equal to 23.8 minus 0.42, which is equal to 23.38. The unit is mmHg. So this is the vapor pressure of water at the given temperature. They have also asked us to calculate the relative lowering in the vapor pressure. So this relative lowering is given by the expression on the left hand side of Raoult's law, which is equal to P1 naught minus P1 divided by P1 naught. So this is equal to P1 naught is 23.8 minus P1 is just now we have calculated, it is 23.38 divided by P1 naught, which is 23.8. This is equal to 0.42 divided by 23.8, which is equal to 0.0176. So therefore, the relative lowering that is observed in the vapor pressure is 0.0176. Let us see a few examples on how we can determine concentrations of solutions. First example, 4.8 gram of NaOH is dissolved in 120 gram of water. Calculate mass percentage of the solution obtained. So we are given with mass of sodium hydroxide as well as water, and we are preparing a solution by dissolving that sodium hydroxide in water. We have mass of sodium hydroxide, that is solute, which is equal to 4.8 grams. Also it's given mass of water, which is solvent, (120 grams). we should find mass percentage of the solution that is obtained. Since they have asked for mass percentage of solution, as the solution is containing solute as well as solvent, we need to calculate mass percentage of solute as well as mass percentage of solvent. We have the formula: mass percentage of solute is equal to mass of solute divided by mass of solution into 100. I'll write this as equation 1. Similarly, mass percentage of solvent is equal to mass of solvent divided by mass of solution into 100. I'll write this as equation 2. So we know mass of solute and mass of solvent, that's given to us. It's 4.8 gram and 120 gram respectively. We need to calculate mass of solution. This is equal to sum of masses of solute and solvent. So it's mass of solute plus mass of solvent. Mass of solute is 4.8 grams. Mass of solvent is 120 grams. So therefore, mass of solution is 124.8 grams. So now let us substitute these values into equation 1 and 2 to find mass of solute. So from 1, I can write mass percentage of solute is equal to mass of solute, that's 4.8 gram, divided by mass of solution, which is 124.8 grams, into 100. So gram and gram gets cancels with one another. After simplifying, we get the answer as 3.85%. So now we need to determine mass percentage of solvent. So that is very simple to calculate. So the total percentage when you consider the solution is 100. So we can subtract mass percentage of solute from the 100 to get mass percentage of solvent. So here instead of formula 2, I can also write the formula as mass percentage of solvent is equal to 100 minus mass percentage of solute. So writing that mass percentage of solvent is equal to 100 minus mass percentage of solute. So this is equal to 100 minus 3.85%, which is equal to 96.15%. So therefore, for the solution which is obtained by dissolving sodium hydroxide in water, mass percentage of solute is 3.85% and mass percentage of solvent is 96.15%. Example 2. Calculate the molarity of a solution containing 5 gram of sodium hydroxide in 250 ml solution. So let me write the formula for molarity. So we have molarity. It is the number of moles of solute dissolved in 1 liter of the solution. So therefore the formula is moles of solute divided by volume of solution in liters. Let us write what are the things that's given in the question. So they have given us mass of sodium hydroxide, mass of NaOH, they have given it as 5 gram. Also they have given us, we have 250 ml solution. So it is volume of solution given to us, that is 250 milliliters. So now this volume of solution should be in liter to substitute into the formula for molarity. So dividing this by 1000, we will get molarity in terms of liter. So that is 0.25 liters. We need to calculate number of moles of sodium hydroxide. So moles of NaOH is equal to its mass divided by molar mass. So it is 5 gram divided by molar mass of sodium hydroxide is 40 gram per ml. Gram and gram gets cancelled. Dividing 5 by 40, the answer comes out to be 0.125 moles. Now let us substitute all these values into the formula for molarity, and therefore we have molarity is equal to mass of solute, that is 0.125 mole divided by volume of solution in liter, which is 0.25 liter. Simplifying this, we get 0.5. The unit is mole per liter, or the same can be written as 0.5 molar. So therefore, the molarity of solution containing 5 gram of sodium hydroxide in 250 ml solution is 0.5 molar. Example 3. If the density of some lake water is 1.25 gram per ml and contains 92 gram of Na plus ions per kg of water, calculate the molality of Na plus ions in the lake. So let us write the formula for molality, which is number of moles of solute dissolved in 1 kg of solvent. So therefore, the formula is moles of solute divided by weight of solvent in kg. So here we need to find out number of moles of solute to substitute into the formula for molality. So they have given us density of water, which is equal to 1.25 gram per ml. Weight of Na plus ions has been given. Weight of Na plus ions is equal to 92 grams. So they have given it's 92 grams per kg of water. So therefore weight of water, which is solvent, that is 1 kg. So we need to calculate is moles of solute. So moles of Na plus is equal to its mass by atomic mass, which is equal to 92 grams divided by 23 grams per mole, which is equal to 92 divided by 23, it's equal to 4 moles. So let's substitute into this formula. So molality, it's equal to moles of solute, which is 4 mole, divided by volume of solvent in kg. So here it's water, 1 kg. So therefore molality is 4. It is 4 mole per kg or 4 molal. The freezing point of a solution containing 0.3 gram of acetic acid in 30 gram of benzene is lowered by 0.45 degrees Celsius. Calculate the Van Hoff factor. Kf for benzene is 5.12 Kelvin kg per mole. Let's list the things that's given. So the total solution is containing 0.3 gram of acetic acid. So acetic acid is solute here. Therefore W2 is the mass of acetic acid, which is solute. It is 0.3 gram. We have 30 gram of benzene. So benzene is solvent. Its mass is represented as W1. So W1 is equal to 30 gram. So they observe that freezing point was lowered by 0.45 degree centigrade. This is also equal to 0.45 Kelvin. So this is the depression in the freezing point, which is delta TF. Also they have given us the value of Kf for benzene, which is 5.12 Kelvin kg per mole. So now we have the formula. The molar mass of solute M2 is equal to Kf into W2 into 1000 divided by delta TF into W1. Substituting, Kf is 5.12 into W2 is 0.3 into 1000 divided by delta TF, which is 0.45 Kelvin, into W1, which is 30. So after simplifying this, we find that molar mass of the solute is 113.8 gram per mole. So this is the experimental molar mass, but the normal molar mass of the solute, which is acetic acid here, that's formula is CH3COOH. So this is equal to 2 into atomic mass of carbon, that's 12, plus 4 into atomic mass of hydrogen, 1, plus 2 into atomic mass of oxygen. So we have 24 plus 4 plus 16 into 2, that's 32, which is equal to 60 grams per mole. So we observe there is a change in molar mass of acetic acid in the experimental value. So we need to calculate Van 't Hoff factor, which is I, that is the ratio of normal molar mass to the observed molar mass, which is calculated by the experimental value. So that is observed molar mass. So substituting into this formula, we have normal molar mass, which is 60 grams per mole. But experimentally, we observed that mass of acetic acid is 113.8 grams per mole. So the unit gets cancelled. 60 divided by 113.8 is equal to 0.53. And therefore, the Van 't Hoff factor is 0.53. Calculate the osmotic pressure of 5% solution of cane sugar, which is sucrose, with the formula C12H22O11 at 50 degree centigrade. So we have the formula osmotic pressure pi is equal to W2 into R into T divided by M2 into B. So from the question, they have given us 5% solution of cane sugar, which means that we have 5 gram of sucrose in 100 gram of water or 100 ml of water. So I can write weight W2 of sucrose, which is 5 gram, and the value of R is 0.0821 liter atmosphere per Kelvin per mole. So temperature they have given us as 15 degree centigrade, which is equal to 15 plus 273 Kelvin, that's equal to 288 Kelvin. And we need molar mass of solute, that is sucrose, which is 12 into atomic mass of carbon, that's 12, plus 22 into atomic mass of hydrogen and 11 into atomic mass of oxygen. So we have molar mass M2 is equal to 342 grams per mole. Also they have given us volume of the solution, which is 100 ml. So when we convert this into liter, that comes out to be 0.1 liter. Now let's substitute all these things into the expression for osmotic pressure. So therefore, osmotic pressure pi is equal to W2, that's 5, into R is 0.0821 into T, which is 288, divided by M2, which is 342, and volume, that is 0.1 in terms of liter. After simplifying this, we get the osmotic pressure of the solution as 3.457 atmosphere. Consider an example. Henry's law constant for the solubility of methane in benzene at 298 Kelvin is 4.27 into 10 to the power 5 mmHg. Calculate the solubility of methane in benzene at 298 Kelvin under 760 mmHg. So we have Henry's law given by, so the mathematical representation is P is equal to KH into chi, where P is the partial pressure, KH is Henry's law constant, chi is the mole fraction. So in the question, they have given us that Henry's law constant, which is KH, is equal to 4.27 into 10 to the power 5 mmHg. Calculate solubility of methane in benzene at 298 Kelvin under 760 mmHg. So the pressure P is given. It is 760 mmHg. So we need to calculate solubility. So here solubility is given in terms of mole fraction chi. So rearranging the mathematical expression for Henry's law constant, I can write chi is equal to P divided by KH. Substituting the values, P is 760 mmHg. Henry's law constant is 4.27 into 10 to the power 5 mmHg. Simplifying, 760 divided by 4.27, it's equal to 177.98 into 10 to the power minus 5. So this can be approximately written as 178 into 10 to the power minus 5. So this is the mole fraction of methane in benzene at 298 Kelvin. On dissolving 2.34 gram of solute in 40 gram of benzene, the boiling point of solution was higher than that of benzene by 0.81 Kelvin. Kb value for benzene is 2.53 Kelvin kg per mole. Calculate molar mass of the solute. So they have given that on dissolving 2.34 gram of solute in 40 gram of benzene. So 40 gram is weight of benzene, which is solvent. So therefore it is represented as W1, and weight of solute is represented as W2, which is 2.34 gram. So they told that boiling point of solution was higher than benzene by 0.81 Kelvin. Means we observe an increase in the boiling point, which is elevation in boiling point, represented as delta TB, which is equal to 0.81 Kelvin. So they have given us the value of Kb for benzene, which is 2.53 Kelvin kg per mole. And we need to calculate molar mass of this solute, that is M2. So we have the formula from the elevation and boiling point. The molar mass of solute M2 is equal to Kb into W2 into 1000 divided by delta TB into W1. Substituting all the values into the formula, Kb is 2.53 into W2 is 2.34 into 1000 divided by delta TB, which was 0.81 into W1, that is 40. After simplifying this, we will get the molecular mass M2 is 182.72 gram per mole. So therefore, the molar mass of solute is 182.72 gram per mole.